Yeah, okay, good. So now let's talk about, we talked about regression, multilinear regression, and these beautiful, beautiful matrix illustrations or algebraic formalization that makes things a lot easier for us when it comes even to derivations. So we're going to see, you know, derivations and backpropagation, all of that. So these are key to, you know, like machine learning and also deep learning. So reaching the classification, supervised classification problem. So this is also another reminder. So similarly to, it's very similar to the regression problem. So basically we want to predict a model or estimate a model. And this model will allow us to design what we call a decision boundary, okay? So a decision boundary where, you know, like we have X tilde transpose W equals to 0. So X tilde is also the compact form where we have the bias. So as I mentioned earlier, so X tilde is 1 and you have X1 to XD. Okay, so it's D plus 1 dimensional vector. And moving forward here, classification, the goal is to predict basically the sign of this, you know, when we project the point, we want to know the sign of this basically, okay? So onto the hyperplane. So when we say the sign, is it negative or positive? So which means that when we do classification, we are actually coloring the space. And I will give you an illustration in a bit. So this is the typical, you know, like softmax loss that we minimize. So if you guys haven't seen this before, please watch the you know, the machine learning blinks on the Bosera YouTube channel. So we explain how we actually derive this, how we define this, why is it a projection first. Second, we explain why the y is a sign. And third, we also cover the loss function and variations of the loss and how to even optimize them. So including, you know, simple perceptrons, you know, like simple classifiers, Bayesian classifiers, and also SVM. So all of these are in the blinks. So make sure you watch those if you haven't, if you don't have a solid background in that, understanding the math, the optimization, and how classification formalization came about in terms of linear algebra, okay, the whole etiology and the evolution trajectory. So now basically, as I mentioned, just a reminder, a simple reminder, when we do regression, you have the input data here in the output. So we want to model the relationship between these two. So it's about capturing how these are connected, okay? So as for the classification problem, it's completely, it's a different space, okay? So in the classification space, we have here the features. So let's say we have two-dimensional features, X1 and X2. So X1 and X2 could be two features that we extract of two classes. And these two features, if they are very well representative, right, of the data characteristics, then when we plot our points, we can easily disentangle them. So let's say, for example, these represent dogs, okay, and these represent cats. So what happens here is that each point is represented by two values, X1 and X2, and these are the original features that we have, okay? So interestingly, when you have very good features, extracted, and you have a good intuition about which features to extract, you can create a space where both classes become easily separable and sometimes linearly separable. So let me just use a regular line here. So this is my model, and this is bad classification because I want my model to maximize the space or the margin between these two classes. So if I want to start with a W and I project my data onto this, basically, you know, like we're gonna get a line like maybe around here. So that's my optimal model. Now, all data above this line will be labeled as +1, for example, okay? and all data below will be labeled as -1. So what does that mean? It means that the label, all right, the label, let me write this down. So the label is the color of the space. The label Y is the sign, okay, or the color of the space, which means I partitioned my R2, my two-dimensional space, using this line here into two parts or two subspaces. And any point, any testing point that will appear here in the future will be colored blue, which means it will have the label 1, and any point that is below the line will have the label brown. So I may make mistakes, and of course I'll make some mistakes during training, especially during testing more, even more. But let's say, for example, I mislabeled this guy. So I put it, it's actually brown sample right here, but I colored it, as I put it in the blue space. So this is a mistake, and this is the mistake that we want to minimize. We want to minimize the error between the predicted label, as usual, and the ground truth label, yi. So we want to minimize the distance between yi hat and yi. And then this is my sample xi that was mislabeled during, for example, training or testing, okay? So as I mentioned earlier, we have lots of losses. So this is one of the losses that we can optimize. And so we project and we take, this is, we're trying to, I find the optimal hyperplane that will separate out the data, and then by optimizing this softmax loss, we can get the optimal W. So for you guys to understand, as I mentioned, how this came about, why we have a log, y1 plus, etc. What's this function? What is it doing? You can check the blinks, the machine learning blinks on the Basira YouTube channel. So now we're gonna go to the nonlinear classification. So for the nonlinear classification, it's very simple. So we go from learning a model that separates the data linearly to learning a transformation or a nonlinear model that separates the data nonlinearly. And in this case, it's the same formula. We don't change anything except for the x tilde is replaced with its transformed feature vector f tilde or function, and this is how we rewrite the whole thing. So we have the model, which is here nonlinear. So when we say the model, it's very important, guys, to separate things out. So model is what we want to learn. So it's actually this line, all right? The y is what we want to predict. So that's the label. And the loss is what we want to optimize. So how does it work? So usually you write the loss. Okay, so you have the model. You write the loss, you optimize the loss. Once you optimize the loss, you're gonna get your optimal model, your optimal theta, right? And then once you get your optimal theta, you can plug it in with all the parameters of your f and get the predicted hat, and that would be step 3. Okay, so this is how it works in optimization of machine learning models stepwise. And if you guys don't know that, so you can also watch the gradient descent. I think it's Blink lecture 4.1 until 4.4. So you can watch those two. Great. Now I'm going to give you an example here. So this is an example. So we have a synthetic example where we have an elliptical decision boundary. So you guys can see it's an elliptical decision boundary. Well, it's an ellipse, all right? So here we go. This is our decision boundary. And the decision boundary here, the formula is F transpose. Okay, so in this case, what do we have here? So in this case, we have a kind of a circle, and it's really difficult. It seems difficult to separate out, right? Like, it's kind of one class. The red points are class 1. The blue points are class 2, and we divide the space into 2 colors as usual. We divide the space into, the points inside this circle that will be colored in one, will have one label, -1, for example, and the other one like +1, for example, okay? So, and here we live in a 2-dimensional space, so each point is represented by 2 features called x1 and x2. So let's look at our model. So our model is handcrafted. So we defined it manually. And this is the formula of our model. So what I want you to do, guys, is to take a minute just to complete these question marks right here. The theta, the expression of F1, the first transformation model, F2, and the theta, which is the internal and external parameters, all parameters that we do have that we need to optimize, okay, in this model that we define right here. So we can start maybe by writing the theta. So we have W0, W1, and W2, right? And for the, W1, we have F1, and we have, for W2, we have F2, okay? So basically, this is x1, the first feature squared. We take the first feature and we square it, and we take the second feature and we square it. So both of them are quadratic transformations, the same type, because it's quadratic, but we transform these two, basically each feature individually, all right? So, and now what happens is that, interestingly, if you guys look at this, right? So in, this is, the data in a 2-dimensional space. Once we transform the space, so we do the right transformation, we have the right transformation. So we apply this transformation here, transform or map into a new space. And this space basically is based on the equation of this nonlinear perfect boundary that we have, right? Then in this new space, we're going to get a line. And it's the same story. So when I say x1, x2 here, when we apply f1 of x and f2 of x, which is the squared, and we put these as new coordinates, what happens, interestingly, and you guys can simulate this. You can write small code in Python to do this, right? It's not difficult. And you can see the distribution. These Jupyter notebooks are available, I believe. So I'll share resources with you guys later. So yeah, so basically what you notice is that the relationship between the data changes. And now we split the space into basically 2 parts. And these are linearly separable by a hyperplane, which is beautiful. So what did we do here? We simplified the problem. If we get the right, as usual, if we get the right transformation formula, if we get these, if we can learn these, if we can get a good approximation of these, the data in the new space will be linearly separable, which means here I can simply apply a linear, classifier to classify this. They're very easy to separate out, okay? So that's that. Now we can look at this. This is another example in a higher dimensional space. So you guys can see that here actually you have an ellipsoid, right? So you have 2 features, and you go from a dimension of R3. So these are the labels. The labels actually are in a very, they are kind of spread out, right? So you have all of these points fitting into this kind of circle, right? This ellipse right here. But when you map into when you do the transformation and you have these 2 as new, as a new basis, as a new coordinates, what happens is that as if you are squeezing all of them into one line, and everything becomes separable by a single line right here. So this is what kind of happens geometrically in a higher dimensional space. Okay, cool. So now the last part of this, and we talked about linear classification, nonlinear classification, right? And now we're going to talk about multi-class classification. So it's a generalization. So remember, guys, we talked about multi-regression, right? Multiple regression. So it's the same story. So instead of having a single label, and you know, labels belong to -1 and 1. They are like they are integer numbers, or they don't live in R. So it's not like, it's like a special version of regression. You can think about classification that way. So here, what we have a sample, and we have a bunch of labels. So we have multiple labels. We have C labels. So what could these labels be? So for example, if we go back to the, you know, like, let me draw an image. So for example, I have an image right here, a figure. So let me put it, an image, and then you have a tree, and you have a house, and you have another one, you have a tree, and you have, for example, birds. Okay, so here I have 4 classes. So I'm gonna put them vertical, like horizontal. So let's say tree, house, bird, and sun. If I take the first image and I put labels, is there a tree? Yes. Is there a house? Yes. Is there a bird? No. Is there a sun? No. I don't see it, right? So the second one, the second image, which is this one, okay, so x2. So here x2 is the ID of the image. So if I do x1 is first image, okay? And this belongs to our, so these are the labels, and the label here, y1, belongs to R4, and y2 belongs to R4. We have 4 labels. So tree, yes, house, no, 1, and 0. You guys get it, okay? So basically it's the same thing here. So what we have, we just, you know, generalize this to C classes, and we do construct, you know, C linear models. Now we had before that regression models. Now we have C linear models of this form. So the WC now maps each, you know, each feature vector or sample onto its corresponding class. So we have, this is my feature vector right here, right? And then I multiply it by the first class, and I get the label of the first class. When I multiply it by the second class, I get the label of the second class, until I get to the last class C, and I get the label, the predicted label of the class C. All right, that's how it happens. And it's the same, you know, it's interestingly very similar to regression, as you guys can see. So everything is so simple, actually. And the goal is here is that, you know, how do we actually get, you know, like this label, is that now we're taking the argmax across all these of this model. So of this, you know, kind of prediction. So every time we're trying to predict, you know, like the value of the y that we want to have using this transformation W. Okay. So later on, we give so given a data set where, so it has samples xi, and for each sample we have the yi. So we have n samples here. Each sample lives in a d-dimensional space, so we have d features, and we have C classes starting from 0 to C minus 1. So we can optimize this using what we call a multi-class softmax loss, and this is a generalized version of the 2-class loss. So we have 2 classes before, now we have multiple classes, and we generalize this to basically C classes. And once you get to that, so once we have this formula, we just optimize it also using gradient descent. So it's actually very straightforward to, you know, like kind of use gradient descent on this loss to get the optimal W and here it's our matrix that we want to estimate. So once we get this matrix, we can easily predict all classes at once. So it's very similar to what we had previously. So now I'm just going to wrap up quickly with this. So we have, now we talk about nonlinear classifiers. So for nonlinear classifier, we have multiple types of classifiers, and we have BC. BC is actually the new dimension, and it's the same formula, guys. So what we have here, it's very simple. So we have our, let me change the color because I use a different color. So if we use pink, all right, so we have the first one, the first, mapping transformed features, and then we multiply them by the weights, right? And we have 1 here for the bias. So this is the bias. We always add 1 to the bias, so we account for a bias in the data. And this is our vector. So basically, this is how we express in linear algebra this formula. So you have F transpose WC for class C. So this is for a single class. So we have a model for each single class. So which means we learn this for every single W right here. So for each W, so I have a WC, I learn, the particular transformations that we need to have, because you may have different classes. And as I mentioned earlier, you guys, in the figure, if you have different classes, you need to kind of, have different models. So let's have a look at this together. So for example, this is a very nice example. So we have 3 classes here, right? So in this example, you guys can see that we have 3 models. So we have the first line, right? The first model right here. And then we have the second model. And we have the third model. And all of these are linear. So now we're learning linear models. And if we learn these lines properly using the multi-class softmax, we can separate the space like this into different segments, but many of them will not be good, right? So, some of them will not give you some good results. So you're going to have a lot of errors over there. But here, with this, with these different models, what do you guys notice? So now we have nonlinear models, because the relationship between these samples may not be that linear, right? So a linear model would fail. But if you use nonlinear models, we'll have like the first one, F3, which looks like this. Okay, so this is the first equation. And this is the second model, which is F2 transpose W2, so with the parameters that we learned. And then the last model, so now we're allowing to learn the last model for each class, right? So this is the last model. So this one also still makes mistakes, right? Because this area is not that good. So now let's look at the third model. So visually, and then we'll read what's going on. So this model, now we're using the same type of model, the same type of nonlinearity, the same type of transformation, and we have these models, and the last one is the green. Okay, so if we look at outside the special model, so for 3, I see that now I have I'm making less mistakes, right? For this one also, I'm making less mistakes, so I'm segregating out better. And then you have also the blue ones over there, the outside areas. So these are completely teased apart. They're not in the overlap. So here in these 3 examples, we can see that a linear model doesn't give you really good results. Here, each classifier uses its distinctive or distinct feature transformation. So we have, as I mentioned, BC here transformations. So because we're mapping into BC plus 1, before we had B plus 1, if you guys remember. So now we change it, we have a transformation for each classifier. And if we use different transformations for each classifier, and we have different types, linear, quadratic, and other types, right? In this example, particular example, you don't get good results. And when you have all classifiers sharing the same nonlinear transformation, so the same type of nonlinearity, for example, all of them quadratics, in this example in particular, you can separate out better. So maybe what could be the reason that this has failed? It could be that first, the data distribution came in a way that it fits the shared top, this type of nonlinearity. So when it's shared, it models better. It could be also, the second reason is that when you have a lot of degrees of freedom, a lot of flexibility, your optimal solution, your theta star, okay, that has the parameters of all of like this model, right, these lines, right, the theta star will not be very optimal. It could be a local minima in the loss, and when it's a local minimum, like something like this, right, so this is a local minimum, this is not a good minimum over here, then it could explain why it didn't go well. So it could be local, it could be in the optimization, it could be that we have a lot of freedom because now instead of having one type, we have 3 types, right? So having all sorts of combinations, what is the best combination is hard to find, and you may get stuck in a local optimum. All right, so there are many reasons to explain that, but it needs further investigation and it needs a lot of toy examples. So now, yeah, so just to wrap up this part, so we have basically, we can have the same, the nonlinear models, and we can do the multi-class softmax for these. So what we need to do is basically change a few things here. So first we have BC, right? So that's the number of classifiers, and then here in this equation, we need to change, it's the same equation, the x with f, and we have the same loss for the nonlinear model, basically, so simple, right? So yeah, so this is another example. So here are multi-class data with elliptical boundaries. So you guys can see that we have, in this space, we have 3 classes, so it's multiple classes. And if we look at the boundary, we would want to put these together visually. So this is what happens over here. And on the top, we do have a very nice separation, but in the bottom, we do one class classification. So one versus all, which means, when we do one versus all, it's just, you're trying to identify one class with respect to the other. So here, for example, it seems that we're trying to identify the green versus the other. So we got the green right versus the other. Here, we're trying to identify the red versus the other. It's not that good. So this model is not good. So which means, what does it mean one versus all? So we have seen this also before. So one versus all, if it means like you have multiple classes, right? So we have 1, 2, 3, let's say 4 classes. So one versus all, it means you turn this problem, this 4 class problem, into a 2 class problem, which means if I take 1 as my first class, anyone else, if I am 2, 3, and 4, I will have the label, for example, 0 or -1. That's what it means, once versus all. So you can see that with the red one, it doesn't get it right. And with the blue one, it's not that bad. I mean, it gets the blue well if you take the outside of this boundary. All blue points are kind of outside. So this one is not that bad here. It's actually one versus all because this is in the middle. So one versus all definitely fails for this area. Definitely, because if you are inside, like you have green inside, if you're trying to go outside this boundary, right? You're gonna get all blue points, and that's not good. So you see, guys, like when you have multiple classes and it's nonlinear, one versus all could be the worst solution. And here you can see that this is, the original data. We have some training samples over here. So these are our training samples that we selected for training, and the validation. So we split the data into a train set and a validation set. So we hit some points like these guys right here, okay? And what you notice is that this is the misclassification. This is our loss. So this is the blue one is the loss on the training, and the orange one is the loss on the testing data. And you guys can see that you know, after a few iterations they have there is a good performance, so it's not that bad. So it's kind of, you know, both of them are quite close over here. Okay, and you can see as you train at the beginning, you have really very large error. And as your model gets optimized, right, at the beginning, you have not a very nice, so it kind of, you know, becomes better and better and better. So, you know, your model is getting better at finding the right boundary. The first approximation is a simple circle, almost.